Hi students, Professor Nugent here. In this video, we're going to introduce multiple regression estimation. With the simple regression model, the key factor that we need to make causal inference or ceteris paribus, all else equal conclusions about how X affects Y is this assumption that all other factors affecting Y contained in the error U are totally unrelated to X, which is completely unrealistic. With multiple regression, what we can do is bring in the factors that are contained in U that by definition affect Y and are correlated with X into the model. And by doing so, by controlling for these other factors, we then have a more compelling case to make these ceteris paribus conclusions, to make causal inference. Let's look at an example. All right, let's think about this wage model where we're predicting wage based on the level of equation, the level of education, and we have discussed other factors that might be useful for predicting wage, but may be related to the level of education. So this example is wage equals to beta naught plus beta 1 times education plus beta 2. Let's bring in this variable experience. All right, plus U. Here's our example regression. So if this is our population model, and education and experience are the two things that matter for wage, experience and education, these two things are correlated, it becomes difficult to make ceteris paribus conclusions. So all else equal, or causal inference, about how education affects wage so the effect of education on wage if we were to leave experience out. So if we were to run the following regression, wage equals, let's do tildes, beta naught tilde plus beta 1 tilde education. So if we were to instead run this, because what we need to make this causal inference is that plus U, all else is being held equal. So we want to say for an additional year of education, how much higher do we expect our wage to be? And in order to make that conclusion, that causal inference, that the cause of the additional year of education or the cause of the increase in wage is the additional year of education, all else has to be equal. But if we are leaving out experience, then what we're capturing here is in fact something of a composite of the effect of education and experience, because as education goes up, experience is also going up. So all else is not equal. So we're failing to make this ceteris paribus conclusion. And in the next video, we're going to actually specify by how much this coefficient is biased. All right, so in general, we can specify a multiple variable regression model, or a model with k independent variables. And this general model we can write down as y equal to beta naught plus beta 1 times x1 plus beta 2 times x2 plus all the way through beta k times xk plus u. And if we wanted to write this at the observation level, we can just write yi plus beta naught plus beta 1 times x1I plus beta 2 times x2I, all the way through beta k, xki plus ui, and now it's at the observation level, where beta naught, this is our coefficient on the constant, or the intercept. And all of these coefficients, the beta 1, beta 2 through beta k, these are our coefficients on their respective variables. So this is like the slope of variable 2. I'm going to refer to this as the coefficient on variable 2. All right. And so on. These are the partial effects. Okay, these coefficients, these are the partial effects. Do observe that this model with k independent variables, this is linear in parameters. However, we can have some nonlinearity in the data, where we can have log transformed data, or we can have polynomials in the data, we can have interactions, but the model must be linear in parameters, and that's what we have here. And the key assumption for the general multiple regression model, the key assumption is the zero conditional mean assumption. Expected value of u given x1 through xk is equal to 0. So the stuff contained in u is unrelated to any of the independent variables. All right, that's our key that's our key assumption for multiple linear regression. And we will cover all of the assumptions that we need again in a later video. Now, how can we solve for these coefficients? We solve for them the same way we do with simple regression. What we're going to do is minimize the sum of square residuals. So we solve for estimates beta naught hat, beta 1 hat through beta k hat of the population parameters beta 0, beta 1 through beta k by minimizing the RSS, the sum of squared residuals, like so. Here is our objective function. We're going to minimize over beta naught through beta k, sum from I equals 1 to n of yi minus beta naught minus beta 1 x1I minus all the way through beta k x k I squared. All right, solve for the first order condition and the second order condition. And we get the result that the ordinary least squares estimates of these coefficients solve the first order conditions. The second order conditions show that indeed these estimates are the minimum of this objective function. All right, and a condition, one of the conditions that we do require to solve these first order conditions uniquely is that n must be greater than or equal to k plus 1. So we have to have a sample size that is at least as large as the number of parameters being estimated. Otherwise, we would not be able to solve for these first order conditions uniquely. All right, let's look at another example. Let's bring in that wage model. We can predict the log of wage and say that we have run a regression and we find that the log of wage is equal to 0.294 plus 0.092 times education plus 0.0041 times experience plus 0.022 times tenure. All right, so experience is the number of years experience, tenure is the number of years of tenure on the job, education is the level of education. This is an example of the model, and we can plug in the values for these variables for an observation to get the predicted log wage. Now, in the future, we will use the language of regression of y on x1, x2, and x3. Here, this is a regression of log wage on the level of education, the level of experience, and the number of years of tenure. Great. All right, so let's do one more thing, and let's talk about interpreting the ordinary least squares regression equation. And we'll come back to this model so we can interpret those coefficients. I want to talk about interpretation. So beta naught, our intercept, quote unquote intercept, we're in multi-dimensional space, so the idea of an intercept is kind of hard to visualize, but we can think of it as an intercept, or more generally, it is the coefficient on the constant progressor. This is the value of y when x1 through xk are all equal to 0, all right? And then the beta 1 hat through beta k hat, these are the partial effects. Now, what does that mean, partial effects? Let's write down some math. So you have a predicted value for y is equal to beta naught hat plus beta 1 hat x1 through beta k hat xk. Now we can rewrite this in terms of first differences. The change in y hat is equal to beta 1 hat change in x1 all the way through beta k hat change in xk. And if we are trying to make ceteris paribus conclusions with respect to variable x1 on y, then all else equal implies that the change in x2 through the change in xk are equal to 0. So this wipes out, and what we have, ceteris paribus, all else equal, so that the change in all else equals 0. Beta 1 gives us the change in y per given change in x. And if that's equal to 1, then beta 1 hat gives us how much y changes for a 1 unit change in x. Let's return to our example for some interpretations using numbers. We have log of wage hat, and that's equal to 2.284 plus 0.092 times education plus 0.0041 times experience plus 0.022 times tenure. All right, so what does this coefficient tell us, the 0.092? That tells us for one additional year of education, implies that 0.092 times 100 gives us a 9.2% increase in wage. And why do we multiply it by 100? Because this is log of wage. All right, that's it, interpretation. Thanks, folks.